Welcome back to the last lecture video for Math 132 for this spring. This is the lecture of 5.1, Area Between Curves. For this first example, we need to find the shaded region here, this quadrilateral region. There's a couple ways to do this, but the first thing that we're going to need to do is we're going to need to find the values of these intersection points so we know where our integral bounds are. Let's go and label our functions y1 and y2. And now let's set y1 equal to y2 to find our first intersection point right here. So to get that, we have x plus 1 is equal to 4 minus 2x, or subtract the 1, add the 2x. So we have 3x is equal to 3, or x is equal to 1. So the x value on this point is 1. To find the y value, we're going to plug back in for y. So we have y2 is equal to 1 plus 1, which is 2. So then we know that the coordinates of this point right here are 1, 2. To find this intersection, we're just trying to figure out where y1 is equal to 0. And that happens at x equals 2. So this is the point 2, 0. Now, let's go ahead and find this area by splitting it into two regions, area 1 here and area 2 there. And the reason that we need to do that is because area 1 has y2 as its upper bound and y1 as its lower bound, whereas area 2 has y1 as its upper bound, but it has y equals 0, the x-axis there, as its lower bound. So the A1 and A2 are defined differently, so we're going to need an integral for each one of those areas. Area 1 here can be found by calculating the integral from 1 to 2. If I'm integrating in terms of x, our x boundaries are 1 and 2, and our top bound is going to be x plus 1, and our bottom bound is going to be 4 minus 2x, and those are the lines for y2 and y1. Now, how do I know that to do the subtraction? Well, what I'm looking for here is, let's imagine that we were building little rectangles inside of area 1 and area 2, and we were going to do a Riemann sum to calculate those areas. And for area 1, the height of this rectangle is the y value for the top of the rectangle, which is x plus 1, minus the y value for the bottom of the rectangle, which is the y1 value, which is 4 minus 2x. So this entire quantity right here is the height of little rectangles in there. And then when we multiply by our dx, well, that is our width. And that is this little infinitely skinny region right there. That's our delta x. So our integral then for area 1 is shown here. We can simplify one step to make the integration a little bit easier. We get 3x minus 3 dx. And when we find the integral, we get 3 over 2 x squared minus 3x evaluated from 1 to 2. And that gives us 3 over 2 times 2 squared minus 3 times 2. That's the antiderivative evaluated at 2. And now we need to do the antiderivative evaluated at 1. And if we go ahead and simplify that, we end up with 6 minus 6 minus 3/2 minus 3, and we get positive 3/2 when we simplify all of that out. So area 1 is positive 3/2. And this checks out. If we take a look at this triangle, the height of this base is 3, and the length of the base is 3, and the height here is 1, and so the area is 3/2 by the triangle area as well. So our integral calculation makes sense. Now let's calculate area 2 doing almost the same thing, except we're going to integrate from 2 to 4, because we're going from 2 right here all the way over to 4. And now the height of our rectangles is determined by y2 minus 0, because now the x-axis is the bottom boundary of the region, and we're integrating in terms of x because we've chosen our infinitely skinny dimension on our Riemann sums to be our x dimension. And when we calculate this integral, we get x squared over 2 plus x, not plus 1, evaluated from 2 to 4. And if we go ahead and simplify that, we get 16 over 2 plus 4 minus 4 over 2 plus 2. And that gives us 12 minus 4, which is equal to 8. And so altogether then, our total area is 3/2 plus 8, or we might think of that 8 as a 16/2, and we get 19/2 is our most simplified complete answer there. I'll give you a second to take a look at that work. And while you're doing that, it is worth noting that you can find this integral by integrating in terms of y, and I'll show you that calculation, but I'm not going to go through the work. Feel free to ask a question on Piazza if you have any questions about this. And there's our integral in terms of y, if you wanted to think about that in terms of y instead. We'll do that more carefully in the next example. All right. So for example 10 here, we have to integrate in terms of dx because that's the only way that these rectangles make sense, where our upper bound and our lower bound are both defined by the curves. It would be a lot harder to integrate in terms of y, because then we would have these weird regions where we would have split Riemann rectangles, and that's not any good. So what we need to do here is we need to integrate in terms of x, because if we were doing these rectangles, we would have x as our infinitely skinny dimension, so that's how we know we need to do things in terms of x. The main trick to this problem is that we're going to have to switch our integral when these curves cross, because if we just did y1 here minus y2 for all of our heights, we would be getting a negative area when they switch. So we're going to have to do two integrals. We're going to have to integrate from 0 to whatever this boundary is, and then from this boundary to our 0 of y equals 4 minus x squared. So let's go and figure that out. So we have that x squared is equal to 4 minus x squared. So 2x squared is equal to 4. So x squared is equal to 2. So x is equal to plus or minus the square root of 2. We're not dealing with the minus version here because we're dealing with positive x values. So x is equal to square root of 2. So that is our x coordinate of this point. And now if we plug square root of 2 into x squared, of course, we get that y is equal to 2. We don't need that y value for this particular problem. And then we can find this point right here. We're trying to figure out where the second curve is equal to 0 to find the roots, and we get that is at x equals 2. So this is the point 2, 0. Now, using that information, we can cook up the integrals for our areas quite quickly. We're going to have the integral from 0 to square root of 2. That's this first area right here. And for the first area, our y1 function is the top up here, and the y2 function is the bottom. So we're going to go ahead and we're going to do our y1 function as the top quantity in our heights, and the y2 function as the bottom quantity in our heights, and then our integration variable is x. And then we're going to do the integral from square root of 2 to 2 to calculate a2. And now we're going to need to switch our upper and lower bounds because our functions have switched which one is on the top and which was on the bottom. So we're going to get an x squared minus 4 minus x squared dx for area 2. And now it is okay if you forgot to switch these and you just did the top minus the bottom all the way through and you didn't really pay attention to which one was actually on the top and the bottom. And all you would need to do is you just need to take the absolute value of each chunk because we're finding a total area. And I've already made sure that we're going to get positive values by making sure that I chose the top function to be the first part of our integrand. So I'm not going to have to worry about absolute values. But you could just do whatever function you wanted and then just take the absolute value. All right, so let's calculate these integrals now. We have 0 to square root 2 of the integral of 4 minus 2x squared dx plus the integral from square root 2 to 2 of 2x squared minus 4 dx. dx. And when we integrate these things, we get 4x minus 2/3 x cubed integrated from 0 to square root 2. And then we have 2/3 x cubed minus 4x evaluated from root 2 to 2. If we go ahead and plug these values in, we get 4 root 2 minus 2/3 root 2 cubed. We're going to have a minus 0 for our second term, so I'm not going to write that. Plus 2/3 times 8 minus 8. I plugged in a 2 here. That's 2 cubed. And this is 4 times 2. Minus 2 over 3 root 2 cubed minus 4 root 2. And we're going to take that whole quantity right there and subtract it and add it to the first one. So let's go and simplify a little bit and see where we get. We get 4 square root 2 minus 4/3 square root of 2. Whoops, I did that again. That should have been square root 2 right there. Plus 16/3 minus 8 minus 4/3 square root 2 minus 4 square root 2. And that gives us then 8 square root 2 minus 8/3 square root 2 plus 16/3 minus 8, or 16/3 square root 2 plus 16/3 plus 8. And we'll go ahead and leave it right there. I don't want to really simplify this any further than that. And that will go ahead and be your final answer. You could have left this answer on an exam where you would have had to written out an answer as this line right here without doing any of the simplification. But of course, on the multiple choice exams and quizzes, you'll be able to pick. You're going to have to simplify a little bit to make sure you can identify which one of the answers is the correct answer. All right, so I'll pause for a minute and let you take a look at some of that work. All right, let's take a look at the next example. Looking at this example, you can see that it's qualitatively different than the last example because we're going to want to use y as our variable of integration, because each one of our left to right distances is going to be defined by doing curve x1 here, this first curve, minus x2, this left-hand curve, because we're going from the positive x values to the negative x values. So if we wanted to find the length of one of these lines, we would take this x value and subtract it from the lower x value, and that's how we're going to find, in this case, the width of our little rectangles that we're adding up, and our infinitely skinny height is going to be our delta y. So we're going to be doing this in terms of y. So our functions are already in the right format. They're already x equals equations. All we're going to need to find are the intersection points in order to figure out what our integration bounds are. We're going to do that by setting y squared minus 4y equal to 2y minus y squared. So we get that 2y squared minus 6y is equal to 0. We can go ahead and undistribute a 2y right there to get y minus 3. And that gives us that our intersection points are at y equals 0 and y equals 3. So we have an intersection right here at 0, 0, because if we plug in 0 into either curve, we get 0. And then for our top point, the y value should be a 3. And if we go ahead and plug in 3 right here, we get 9 minus 12, which is a negative 3. All right, now we can cook up our integral. We're going to be doing the integral from 0 to 3 because these are our y values, y equals 0 to y equals 3. And then the right-hand endpoint of each one of these rectangles, or each one of these lines, if you want to think about the rectangles being so skinny that they look like a line, we're going to add up all the lines to find the area. And so we're going to do the right-hand endpoint, which is 2y minus y squared, minus the left-hand endpoint, which is y squared minus 4y. And we're going to integrate in terms of y. I'm going to go ahead and simplify this just one step. So we end up with negative 2y squared plus 6y dy. Now we can find this derivative by doing using the fundamental theorem of calculus. So we'll take the antiderivative, 2/3 y cubed plus 3y squared, and we're going to evaluate from 0 to 3. And when we do that, we get negative 2/3 times 3 cubed plus 3 times 3 squared minus 0 plus 0. So if we simplify here, we get negative 54/3 plus 27, and that gives us negative 54/3 plus 81/3, which is 27/3, which is equal to 9, is the area of this region. So the difference here is that we integrated in terms of y because it's a lot easier to conceive of this area as being a sum of these horizontal lines, because the horizontal lines are easily defined by the right-hand curve and the left-hand curve. All right, let's take a look at the next example. All right, this next example is problem number 7 from the web work. So what we're going to try to do is we're going to try to find the area between these two curves, this linear function and this quadratic function. Let's go and label those. Now let's go and start by graphing these functions. A good trick for graphing things is to find the x and the y intercepts by setting the other variable equal to 0. So with the linear function, if we set x equal to 0, we can see that y must be 4. And if we set y equal to 0, we see that x has to be 16. So that gives us our intercepts for our linear function. Let's go ahead and graph the linear function. So there's our linear function in green. Let's do the exact same strategy for the quadratic function. So if x was 0 on the quadratic function, then y would either need to be square root of 5 or negative square root of 5. And if y is 0, then x must be negative 5. So let's go ahead and graph those points. Now we can kind of see that this is a parabola opening to the right. Let's graph that. So there's a parabola. And now the last thing I want to do is I want to find 3 important points. I want to find the point of the vertex of the quadratic formula, or the quadratic function, and then I want to find both of the intersections of the linear and the quadratic. Well, the vertex of the quadratic is simply negative 5, 0. So we know that point. And now to find the intersection of the quadratic and the linear, we must first solve for x, and then we're going to set these equations equal to each other. So when we solve the linear equation for x, we get that x is equal to 16 minus 4y. And when we solve the quadratic equation for x, we get that x is equal to y squared minus 5. Now what we're going to want to do is we're going to want to set these equal to each other to figure out where they intersect. So 16 minus 4y equals y squared minus 5. And this is a quadratic, so we need to go ahead and get one of the sides equal to 0. So we have that 0 is equal to y squared plus 4y minus 21. And that conveniently factors into y plus 7, y minus 3, to give us that our y coordinates of our intersections are at 3 and at negative 7. If we go ahead and plug our 3 or our negative 7 into either one of the equations, we can get our other coordinates. And when we do that, we see that our first intersection, our y value is 3. If we plug a 3 in right here, we get that x must be 4. And then for our other intersection, our y value is negative 7. If we plug a negative 7 in right here, we get 28 plus 16, and that gives us 44. So my graph is a little bit off right here. Let's go ahead and draw a little squiggle in our graph and say that this is actually closer to 45 out there. I just did not graph this cleanly. Let's take a look at Desmos to see what it actually is supposed to look like. All right, there's our graph, and if we find the intersections here, we see the intersections are at 4, 3, at 44, negative 7, and and this vertex is at negative 5, 0, just like we found. And the shape here is similar to what we sketched, but of course, it's a little bit more to scale when the computer does it. Let's go back to our work. All right, so now that we have this region sketched, we can see that the area that we're looking for is this area in between these two curves. All right, I'm going to go ahead and sketch this area down here, just a rough sketch of it, to show you that when we try to find the area in terms of x, we're going to need to split the integral, because as we go across this intersection point, the function that bounds the rectangles that we would be making to estimate the area changes. From negative 5 to 4, we're using just the parabola right here. But from 4 to 44, we're using the linear function and the parabola. All right, so let's try to work that out in our integral. So what we're going to do right here is we're going to be taking the integral from negative 5 to positive 4 dx plus the integral from 4 to 44 of our functions in terms of x. So now let's go ahead and try to figure out what those functions are supposed to be. Since we're integrating in terms of x, we're going to need to solve our equations to be in terms of y, or to be a y equals equation in terms of x. So for the parabola, we have that x is equal to y squared plus 5. So for the parabola, we have that x is equal to y squared minus 5. If I'm trying to solve this for y, I get that x is x plus 5 is equal to y squared. And finally, y is equal to the positive or negative square root of x plus 5. Well, that's a little bit weird because we have the positive or the negative square root. The reason why is because the top part of this function is the positive square root of x plus 5, but the bottom part of this function is the negative square root of x plus 5. So what we need to plug into our integral then is the top part of the function, the square root of x plus 5, the positive version, minus the negative square root of x plus 5. And that's going to be our height of this little green triangle for this first part of the area. For the second part of the area, we're going to need that linear function solved in terms of y equals. So we have x is equal to 16 minus 4y, or x minus 16 is equal to negative 4y, or y is equal to negative 1/4 x plus 4. So since our top part of our function right here, or the top part of the region, is that linear function, that's going to be our top part of our height. So we get 1/4 x plus 4. And then we're going to be subtracting the bottom part of the square root function, which is negative square root of x plus 5. So let's just simplify one step with our integrals. So we get the integral from negative 5 to positive 4 of 2 square root of x plus 5 dx plus the integral from 4 to 44 of negative 1/4 x plus 4 plus the square root of x plus 5 dx. Now calculating these integrals is a little bit of a mess, but let's take a look at it. Alright, so there's our antiderivatives. And now let's go ahead and evaluate the antiderivatives. Oh man, so when we start to calculate these integrals, things really get to start to get out of hand numerically. But what we want to pay attention here is not all of this numerical calculation. Let's take a look and make sure that we know how to calculate our areas by at least writing the integral right here. And that's the most important part to take away from part B. Part of the reason this problem is sequenced this way is because it's a little bit better idea to integrate in terms of y rather than in terms of x. So if we take a look at the area again, if we had done horizontal rectangles, we have the exact same boundaries on our rectangles. The linear function is the rightmost bound, and the quadratic function is the leftmost bound. So this makes our integral quite easy. Remember, our intersection points were at -7, or we're at 4, 44, -7, and 4, 3. So we're going to be doing the integral from -7 to 3 of the linear function in terms of y, which was 16 minus 4y, and the quadratic function in terms of y, which was y squared minus 5. And now we have a much easier integral. We can simplify this one step. We get the integral from -7 to 3 of -y squared minus 4y minus plus 21 dy. And when we evaluate that, we get -1/3 y cubed minus 2y squared plus 21y, evaluated from -7 to 3. And plugging in these numbers is a lot easier than plugging in those 4s and 44s in the previous answer. I'm just going to go and leave this answer unevaluated. We can plug in those numbers if we want to, and that will give us our area. And these two areas will be equivalent, even though the calculation was quite a lot more simple when we did our integration in terms of y. All right, 2 more examples to go. All right, example 12 is problem number 9 from the 5.1 web work. We're going to need to start by graphing each one of these functions. For the first function, let's do a table here. We have our x values and we have our y values. And if x is 0 or 1, y would be 0 or 2. And we can choose x to be something like 4. We'll also see there that y is 4. Now if we try to graph this, what we're going to see then, we have our values at 0, at 1, positive 2, and at 4, 4. So I have 1, 1, 2, 3, 4. And that's maybe what our graph looks like. So let's go and connect the dots, and we're going to have this curving down square root function. So that's y equals 2 square root of x. Now in green, let's find y equals 3. Well, that's just the horizontal line going through y equals 3. And now in red, let's graph y plus x is equal to 3. We can just find the intercepts for this linear function. If x is 0, y must be 3. If y is 0, x must be 3. So let's go and graph that. So we have intercepts at that 3, that 3. And so this gives us that the area that we're trying to find is this triangular area in between all of these functions. I guess let's go ahead and draw that in there in gray. So we're trying to find that triangular area. Let's draw that just a little bit bigger. So we have this area right here. And notice that if we tried to integrate this in terms of x, we would need to split our integral at that intersection point right here, because our top and bottom of our rectangles, or these vertical lines, would change as we went through that intersection point. In contrast, if we chose to integrate this in terms of y, so that we were using horizontal lines, we're going to have the exact same parts of the function acting as the right and the left hand endpoints. The right hand endpoints are all y equals 2 square root of x, and the left hand endpoints are all x plus y is equal to 3. So that means it probably will be easier to integrate this in terms of y. A couple of important things to notice. This top line right here is y equals 3. That's going to be the upper bound of our integral then. And for the bottom, we need to find this intersection point. So what we're going to do there is we're going to solve the linear function for y. So we get y equals 3 minus x. And we have the quadratic function, or the square root function, already solved for y. So when we set those equal to each other, we get that 3 minus x is equal to 2 square root of x. Let's go ahead and square everything. So we get 9 minus 6x plus x squared is equal to 4x, or x squared minus 10x plus 9 is equal to 0. And we can factor that to be x minus 1, x minus 9 is equal to 0. So you know these things intersect at x equals 1 and x equals 9. This is actually, we can tell that this is the x equals 1 intersection. So that's the point 1. Then we can get our y value by plugging back in here. So we get y equals 3 minus 1. So y equals 2. So this intersection point is the point 1, 2. Now you may be wondering what happened to this x equals 9. We've actually invented a root there, because when we squared it, we invented the other half of this right-facing quadratic, and these functions would have intersected down here at x equals 9. But that's not a part of our function because we're just dealing with the positive square root of x. So our only intersection is at the point 1, 2. What that really tells us is that this value right here, the y value, is 2. So the bottom bound of our integration is going to be 2. Now, what we need to do is since we're going to be integrating this in terms of dy, we need to get both of our equations in terms of x. The linear function is going to be x equals 3 minus y, and the quadratic function is going to be x equals y squared over 4. So, since that y squared over 4 is the rightmost part of the function, we're going to have that be our first part. That is when we're finding our distances, we're going to take the right-hand endpoint minus the left-hand endpoint, which is 3 minus y. And then we're doing our integral in terms of y, so we're going to finish it with a dy. Let's go ahead and make that green, I guess. Okay, so now let's find this integral. We have y cubed over 12 minus 3y plus y squared over 2, evaluated from 2 to 3. And if we plug in our 3 there, we get 27 over 12 minus 9 plus 9 over 2 minus 8 over 12 minus 6 plus 4 over 2. And we can go ahead and leave that as our final answer for our area right there. We don't need to simplify it all. The key idea here is that we need to be able to graph the region and then decide whether or not we're going to do this in terms of x or in terms of y. We decided to integrate this in terms of y because when we're doing that, that means that we're essentially using horizontal lines, and we're going to add up the lengths of all those horizontal lines, and then this infinitely small height that we get when we make that a rectangle, for trying to think about this as Riemann sums. And we're going to then integrate from the bounds of our y intervals, which are y equals 2 and y equals 3, and we got that by taking a look at the intersection. All right, one last problem here. Our last problem is that we're trying to find the area between y equals x. I can graph that one pretty easily. This is our y equals x line. And then we're going to try to graph 4x plus y squared is equal to 12. And I want to do that by coming up with a table. So when x is equal to 0, that means that y must be equal to the square root of 12, plus or minus square root of 12. And when y is equal to 0, that means that x must be 3. So if I go ahead and put some tick marks on here, when x is 3, y is 0. And when x is 0, y is plus or minus square root of 12, which is in between 3 and 4. So our parabola must open left, and the area here is going to be very similar to the area that we found in the earlier example. So what we're going to want to do is we're going to want to integrate this one in terms of x, because that gives us, or in terms of y, because that gives us nice clean rectangles that have the same right hand and left hand functions throughout the entire domain. So if we're going to do this in terms of y, we're going to need to solve our equations to be x equals equations. Our first one's already done. And the second one, we need to just go ahead and subtract the y squared. So we get 12 minus y squared, and divide by 4. So we have that x is equal to 3 minus 1/4 y squared. So our functions are going to be x equals y and x equals 3 minus 1/4 y squared. If we set those equal to each other, we can find the intersection points. I'm going to multiply this entire thing by 4 to get rid of the fractions. So I have 4y equals 12 minus y squared, or y squared plus 4y minus 12 is equal to 0. And then I can see that this factors y plus 6, y minus 2 is equal to 0. So I get that y is equal to 2 and y is equal to negative 6. So I know my intersection points have y coordinates of negative 6 and positive 2. I actually don't need to find the x coordinates at all because I'm going to integrate this in terms of y. So now let's go ahead and cook up our integral. We're going to be doing the integral from negative 6 to positive 2. Our right hand endpoints are going to be determined by this quadratic function, 3 minus 1/4 y squared. And our left hand endpoints are going to be determined by the function y equals x. And then we're going to be integrating in terms of dy. So when we find the integral, we get 3y minus 1/12 y cubed minus y 1/2 y squared evaluated from negative 6 to positive 2. And you'll just need to go ahead and plug in the values of 2 and negative 6 to find that area. And that is going to conclude our last lecture video of Math 132 during this crazy online teaching transition during the COVID pandemic. So now it's time to start studying for your final exam. Make sure to ask your instructors if you have any questions, and good luck with the rest of the class.